Let us look at some properties of eigenvalues and eigenvectors. The constant term of the characteristic polynomial of the matrix A is the determinant of A. We know what the characteristic polynomial is, and we also know from where it comes. It comes from the determinant of A minus lambda I. Now here, minus 1 to the power of n is mentioned explicitly since there is no coefficient for lambda to the power of n to absorb it. See, if anywhere else, if minus is there, it can be absorbed into the C sub whatever. Whereas in case of lambda to the power of n, there is no C. So we have to explicitly mention minus 1 to the power of n. Now, to extract the constant term, because that is what we are talking of here, the constant term, let lambda equal to 0. Now here, lambda is just a variable of this polynomial and not the eigenvalue. Remember, eigenvalue are those values of lambda which are the roots of this equation. If we equate it to 0, then all terms except the constant disappear. And we are left with determinant of A minus lambda has been taken as 0 times I. 0 times I is a 0 matrix. So determinant of A minus 0 matrix equal to C sub n, which means A minus O, that is a 0 matrix, is nothing but determinant of A equal to C sub n. So hence the constant term is equal to the determinant of A. 0 is an eigenvalue of a square matrix if and only if the matrix is singular. So 0 is an eigenvalue. Let's begin with that, which implies, since it is an eigenvalue, determinant of A minus 0i is equal to 0, which implies C sub n is equal to 0, which implies determinant of A is equal to C sub n. So determinant of A equal to 0. And if determinant of A is 0, then A is singular. Now let's look at it conversely. A is singular implies determinant of A equal to 0, which means determinant of A minus 0i is equal to 0, which means lambda is equal to 0 is an eigenvalue. So 0 is an eigenvalue of a square matrix if and only if the matrix is singular. Now the third one. For a given eigenvector, there is only one eigenvalue. So let's see. Let lambda 1 and lambda 2 be two eigenvalues corresponding to the same eigenvector x. Now, which means A times x is equal to lambda 1 times x and A times x is equal to lambda 2 times x. Now, since the left hand sides are equal, right hand sides are also equal, which means lambda 1 times x is equal to lambda 2 times x. Bring it to the same side, we get lambda 1 minus lambda 2 times x is equal to 0 vector. Now, by definition, x, which is an eigenvector, cannot be a 0 vector, which means lambda 1 minus lambda 2 has to be equal to 0, which means lambda 1 is equal to lambda 2. So for a given eigenvector, there is only one eigenvalue. Now, if x is an eigenvector corresponding to an eigenvalue lambda, then for any scalar k not equal to 0, k times x is also an eigenvector corresponding to the same eigenvalue. So a times k times x, which can be written as k times a times x, because k is scalar. Now a times x is equal to lambda times x. So we substitute A times X with lambda times X. So we have K times lambda times X. Now, lambda is the eigenvalue. Let's take it out. And K being a scalar, let's bring it in. So we have lambda times K times X. So which means A times K times X is equal to lambda times K times X. Hence, K times X is also an eigenvector corresponding to lambda. Thus, any non-zero scalar multiple of an eigenvector is also an eigenvector corresponding to the same eigenvalue. Condition K not equal to 0 is required to avoid zero vector, since by definition eigenvectors are non-zero vectors. Fifth, if x1 and x2 are the eigenvectors of a matrix A corresponding to the eigenvalue lambda, then x1 plus x2 is also an eigenvector. Let lambda 1 and lambda 2 be two eigenvalues corresponding to the same eigenvector x. Then A times x1 equal to lambda times x1 and A times x2 is equal to lambda times x2. Now, adding the two equations, we get A times x1 plus A times x2 is equal to lambda times x1 plus lambda times x2. A is common, so A times x1 plus x2 is equal to lambda times x1 plus x2, which implies x1 plus x2 is also an eigenvector because it is in the form of A times the vector is equal to lambda times the vector. Sixth, let V of lambda 1 and V of lambda 2 be the sets of all eigenvectors corresponding to distinct eigenvalues lambda 1 and lambda 2 respectively. Then intersection of V of lambda 1 and V of lambda 2 is the empty set. That means there is no commonality. Remember, V of lambda 1 is the set of all eigenvectors corresponding to lambda 1. Similarly for V of lambda 2. Assuming lambda 1 and lambda 2 are distinct and V of lambda 1 intersection V of lambda 2 is not equal to the empty set, then there exists X such that X is in the intersection of these two sets. That is, it is there in both the sets. Implies that X is in V of lambda 1 and X is in V of lambda 2, which implies A times X is equal to lambda 1 times X and A times X is equal to lambda 2 times X. Left hand sides are equal. That means right hand sides are equal. So lambda 1 times X is equal to lambda 2 times X. Implies lambda 1 minus lambda 2 times X equal to 0. And if the product has to be 0, one of the factors has to be 0. But X is not equal to 0. Therefore, lambda 1 minus lambda 2 equal to 0, which implies lambda 1 is equal to lambda 2. But that is against our assumption that lambda 1 and lambda 2 are distinct. So we started with them being distinct and we arrived at the conclusion that they are the same. So because of that contradiction, we can say that the set of all the eigenvectors corresponding to lambda 1 intersection with V of lambda 2 is equal to empty set. So basically, we arrive at this theorem. Eigenvectors corresponding to distinct eigenvalues are linearly independent. Seventh, if lambda is an eigenvalue of matrix A, with corresponding eigenvector x, then lambda square is the eigenvalue of A square. Remember, A square means what? The square of a matrix. Okay. So let's see how we can prove that. A times x equal to lambda times x. Pre-multiplying by A on both sides, we get A times x is equal to A times lambda times x. So A times A is A square times x is equal to lambda times A times x. Now, A square times x is equal to, now lambda times A times x can be written as lambda times x, because A times x is equal to lambda times x. And we arrive at A square x is equal to lambda square times x, which implies lambda square is an eigenvalue of A square. And in general, if lambda is an eigenvalue of A, then lambda to the power of n is an eigenvalue of A to the power of n. Now, 1 by lambda is the eigenvalue of A inverse, provided A is non-singular. A times x equal to lambda times x. Assume A is non-singular, which implies A inverse exists. And since A inverse exists, left multiply by A inverse on both the sides. So A inverse times A times x is equal to A inverse times lambda times x. Regrouping, we get A inverse times A times x is equal to lambda times A inverse times x. And here A inverse times A is I times x is x, is equal to lambda times A inverse times x. Since A is non-singular, 0 is not an eigenvalue. Hence, lambda is not equal to 0. So, we can divide both sides by lambda. So, when we divide both sides by lambda, what do we get? We get this lambda getting cancelled. So, we are left with A inverse times x. And on the other side, we get 1 by lambda times x. So, again, we have a matrix times a vector x is equal to 1 by lambda times the vector x. That means 1 by lambda is the eigenvalue of A inverse. Determinant of A divided by lambda is the eigenvalue of adjoint of A, provided A is non-singular. So let's start with the fact that A is non-singular, which implies A inverse exists. And we know A inverse can be evaluated using the formula 1 by determinant of A times adjoint of A. Right multiplying both sides by x, we get A inverse times x is equal to 1 by determinant of A times adjoint of A times x, which implies, remember, A inverse x is equal to 1 by lambda times x. So 1 by lambda times x is equal to 1 by determinant of A times adjoint of A times x. Now we can take this determinant of A to the other side. So we have determinant of A divided by lambda times x is equal to adjoint of A times x. Now here I'm just rearranging the equality. Adjoint of A times x is equal to determinant of A by lambda times x. Now that implies that determinant of A divided by lambda is an eigenvalue of adjoint of A. If A is a square matrix, then A and A transpose have the same characteristic polynomial and hence the same eigenvalues. This is pretty straightforward. We know that a matrix and its transpose have the same determinant, and that lambda I is equal to lambda I transpose. So determinant of A minus lambda I is equal to the determinant of A minus lambda I transpose. which is equal to A transpose minus lambda I. Hence, A and A transpose have the same characteristic polynomial and therefore the same eigenvalues. So that was some properties of eigenvalues and eigenvectors. That's it for now.